Thanks so much to the organizers of this event. I've really enjoyed all the presentations so far today. I'd like to launch my own presentation this morning with a brief demonstration of my own dialect of spoken Eva. Uh, First row, Qokeedy, 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 Qokeedy. Second row, Choldaiin, 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 Choldaiin. Now, with that little matter of disambiguation out of the way, my subject today will be a set of observations about the working of Voynichese, centered on what I've been calling the Qokeedy and Choldaiin loops. These two loops came out of an experiment I tried a couple years ago to explore a simple question, namely, given one single glyph of any particular type, what is the probability expressed as a percentage that the next glyph coming after it will be of a particular type? I was curious to see whether there might be any value in approaching the patterns of Voynichese as governed not by a fixed word paradigm with particular slots for glyphs in it, but rather by a glyph process of composition in which each new choice of glyph is constrained by the glyph or glyphs that came before in ways that give the appearance of a word structure as a secondary effect. So with that idea in mind, I'd like to define some relevant terms. First, the step rightward from one glyph to another, such as from K to A, is a transition. We can notate this as K to A to distinguish it from Ka as a bigram. Second, the probability of a transition from one glyph to another, such as K to A, is its transitional probability, not to be confused with the frequency of the Ka bigram itself. The glyph K and the bigram Ka will both have overall token counts in any given section of the text. But that's not what we care about here. What we want to know is if the current glyph happens to be a K, however common or rare that might be relative to other glyphs, what's the probability that the next glyph after it will be an A or an E or something else? Third, the whole set of probabilities of different glyphs following after any one given glyph, such as the probabilities of all different glyphs following after K, constitute that glyph's transitional probability matrix, with the total adding up to 100%. Here's an example of a transitional probability matrix for transitions from the glyph Y. Except I've actually shown two transitional probability matrices side by side, since I found that when we calculate these for courier A and courier B, the results tend to come out entirely different. In courier A, the most common transition from Y is to D, but that's only the fifth most common transition in courier B. Conversely, in courier B, the most common transition from Y is to Q, but that's only the fifth most common transition in courier A. These probability matrices are also incomplete. As you can see, the parts I've shown total up only to around 96 and 97.5% respectively, with the probability of each remaining transition falling somewhere below 1%. Now, we obviously need to make some subjective choices about how to run an analysis like this. So here are the rules I personally came up with, all of which could have been done differently and all of which could be challenged. First, limit analysis to paragraphic text, that is, no labels or radii or circles. Second, disregard spaces. The last glyph of one word is to be understood as transitioning to the first glyph of the next word. Disregard transitions across line and paragraph breaks. We do not count the relationship between the last word of a line or paragraph and the first word of the next one as a transition. Fourth, treat CH, SH, CTH, CPH, CKH, and CFH as indivisible units. For example, we don't treat C as transitioning to H and then on to something else. Finally, evaluate the probability of a transition to any quantity of E or I first and to a specific quantity of E or I second. Here's another example to illustrate how that works. In courier A, a transition from O to I is slightly more probable than a transition from O to CH, even though a transition to any specific quantity of I's is less probable than a transition from O to CH. Similarly, in courier B, a transition from O to E is slightly more probable than a transition from O to S, even though a transition to any specific quantity of E's is less probable than a transition from O to S. This distinction becomes significant when we set about ranking the probabilities of different transitions. Here's a list of the top 2 most probable transitions from each common glyph type in courier B. As you can see, there's often a big drop in percentage between the first and second ranked options. The transitions marked in blue almost always coincide with a space. I call these strong breakpoints. The transitions marked in red often coincide with a space, but often don't. I call these weak breakpoints. The units typically thought of as Voynich's words are split up by these breakpoints, but when analyzing transitional probabilities, I find it works better to treat the text as an unbroken stream that continues across word breaks. After all, even the 2 most prevalent strong breakpoints shown here display a substantial difference in probability between first and second ranked options, approximately 33 versus 26% for N and 28 versus 18% for Y. But now let's see what happens if we start with the most probable transition of all, Q to O at almost 98%, and then follow all the most probable transitions to see where they lead us. O most often transitions in turn to K. K most often transitions to E, and specifically 2 E's in a row rather than 1 or 3. EE most often transitions to D. D most often transitions to Y, and Y most often transitions back to Q with a strong breakpoint between, producing an endless loop, the Qokeedy loop. Of course, this word is among the most notorious for actually repeating over and over again in the text of the Voynich manuscript itself. Of course, at each point in the loop, we could instead have chosen the next most probable transition and then taken all the most probable transitions from there on out. The transition from Q to E is pretty darn improbable, but the result gives us one of the comparatively few attested words beginning with QE, Qokeedy. The transition from O to L gives us Qokeedy. The transition from K to A gives us Qokeedy. The transition from the next most probable number of E's after K gives us Qokeedy. The transition from EE to Y gives us Qokeedy. The transition from D to A gives us Qokeedian Qokeedy. And the transition from Y to O gives us Qokeedy Qokeedy. If we take any one of the second or third most probable transitions out of the Qokeedy loop, which is to say all the transitions with a probability greater than 10%, but otherwise follow all the most probable transitions, we usually get a sequence of 2 consecutive words that actually appear together in the manuscript, often multiple times. And in all cases but one, we get at least one attested word, and even the exception, Qokeedy, with its atypical 2 gallows glyphs, is remarkably similar to 2 other strange but attested words, Qokeoki and Qokeokedi. Meanwhile, if we start with a glyph that isn't part of the Qokeedy loop, such as A, we still end up drawn into the loop if we follow the most probable transitions forward from it, again producing sequences that actually appear in the manuscript, sometimes repeatedly, sometimes spread across 2 or even 3 words. So, longer sequences, which the transitional probability matrices would predict are especially likely to occur, do, in fact, mostly seem to occur. And here's a list of the longest actual identically repeating glyph sequences in the Voynich manuscript, ignoring spaces, a few of which partially overlap one another. Now, when I originally pulled this list together, I wasn't following quite the same rules I described a moment ago. Among other things, I didn't keep track of whether both tokens of each sequence shared the same number of final E's, and I allowed sequences to cross line breaks. But I think it's still a useful data set for present purposes. Here, I've highlighted in green every point at which these sequences choose any transition other than the single most probable one. And here I've noted the rank of each alternative transition. As you can see, they're mostly second or third ranked transitions, or what I've noted here as transition B, which refers to the second most probable quantity of I's or E's. 20 of the 23 sequences contain 3 or fewer divergences from the most probable path. 13 of the 23, still over half, contain 2 or fewer. 7 contain 1 or fewer, and 1 contains no divergences. So the longest identical glyph sequences that actually occur twice or more in the Voynich manuscript mostly follow the path of first-ranked transitions, with usually just 1 or 2 deviations from it. Now, these long repeated sequences are, I should mention, all found in Courier B. But let's now take a similar look at Courier A. In each case where I've highlighted a percentage in green, the first ranked transition is to a different glyph than it is in Courier B. This time, CH most often transitions to O most often transitions to L most often transitions to D most often transitions to A most often transitions to I, and specifically 2 I's in a row rather than 1 or 3. I most often transitions to N, and N most often transitions back to CH, giving us another entirely different loop. So that's where these Qokeedy and Choldaiin loops come from. Unlike Qokeedy, Choldaiin seems likely to be broken into 2 words at a weak breakpoint as Chol and Dain. But that's not the only difference. You might recognize this type of visualization from my Malta presentation or from some of my Voynich Ninja posts. It's designed to show distribution by line and paragraph position. Here, the blue coloration shows the distribution of the O to K transition of the Qokeedy loop in Courier B. As you can see, it covers most of the square. Here's a similar display for the next step in the loop, again with the most probable transition shown in blue. And again, the next step. Remember that white or whitish colors combine all 3 colors together, red, green, and blue. So there's actually more blue here than you might think. The next step, pretty solid blue, and the next step, lots of blue. What I mean to illustrate with these visualizations is that each of the transitions that make up the Qokeedy loop is spread out across the greater part of lines and paragraphs. They share a lot of space in common. But it's different with the Choldaiin loop. Its 2 lowest probability transitions, or weakest links, N to CH and L to D, tend largely to occupy different spaces within lines and paragraphs, consistent with a broader spatial sorting of the glyphs CH and D in Courier A, with CH generally favoring the left and D generally favoring the right. If we look at the top 3 most probable transitions from N in Courier A, we see that there's an area on the right where we might actually expect a Dain loop. And if we look at the top 3 most probable transitions from CH, we see that there's an area on the left where we might expect a Chol loop. There are, in fact, a few dozen tokens of Choldaiin and Dain Chol, and even a few tokens of Choldaiin Chol. But the words Chol and Dain have distinctly different spatial distributions, and it's these 2 separate words, Chol and Dain, that behave similarly to Qokeedy in sometimes appearing 3 times in a row without change. Each of these 3 words, Qokeedy, Chol, and Dain, also represents one of the 3 word series identified by Torsten Timm, centered on the words Chedi, Ol, and Dain, series within which he finds that the frequency of any given word turns out to be inversely proportional to its edit distance from one or more of those three words, with Chedi, Ol, and Dayin themselves having the highest frequencies of all within each group. In the case of Dayin, Timm's series-defining word is the same as the loop word. In the other two cases, the series-defining words are different. Chedi instead of Qokeedy, Ol instead of Chol. But Qokeedy is the word in Timm's Chedi group that most frequently appears repeated identically twice. And Chol is the word in Timm's Ol group that most frequently appears repeated identically twice in a row. In both groups, the most frequently occurring word is not the word most frequently repeated in this way, a noteworthy distinction and one I'll be returning to in just a moment. But first, I want to acknowledge a shortcoming of the kind of analysis I've been discussing so far, and one I'm sure you've already been thinking about in your own minds. First-order transitional probability matrices from one single glyph to other single glyphs are simple and convenient to analyze, so much so that I was able to work out my initial analysis by hand on little slips of paper. But they're probably a little too simple to get us very far. Second-order transitional probability matrices from a given bigram to following single glyphs are more trouble to analyze, and with them I had to turn to spreadsheets for managing the data. But as you might expect, these second-order matrices do expose some additional complications. For example, overall, in Courier B, transitions from D to Y are much more frequent than transitions from D to A, but the relative probabilities of these two transitions from D vary quite a lot depending on the glyph that comes before the D. If that glyph is a CH or any number of E's, the transition to Y becomes even more probable. Note that it's most probable of all after EE, corresponding to part of the Qokeedy loop. But if the glyph preceding the D is L, Y, N, or R, a transition to Y is actually less probable than a transition to A. The probability of a transition from Y to either K or T in Courier B varies greatly depending on what glyph precedes the Y, with the order of these preceding glyphs from lowest to highest probability being identical in both cases. Other cases seem a bit more nuanced, such as transitions of O to R or K in Courier B, but while O transitions more frequently to K overall, it's most likely to do so if preceded by Q, again corresponding to part of the Qokeedy loop, and especially unlikely to do so if preceded by another K. For transitions from O to R, the situation is reversed, and I could, of course, go on. But in spite of all these added complications, the path of most probable second-order transitions in Courier B or Courier A passes through that same pair of Qokeedy and Choldaiin loops as before. So these loops aren't just artifacts of the simpler first-order analysis. I've also experimented with using these second-order transitional probability matrices to generate text stochastically. With the probability of a space between every two glyphs determined by the actual ratio of spaced to unspaced tokens of that glyph pair. Here's an excerpt from a longer text generated using the matrices for Courier B. These raw results look to me about as plausible as the results of any other efforts I've seen to generate Voyniches-like text stochastically, although, of course, they lack any paragraph and line patterning. If we now calculate some statistics for the same longer stochastically generated text, the most frequent words turn out to be Chedi and Ol, two of Timm's three series-defining words, even though the most probable sequence, as we've seen, ought to be Qokeedy. Indeed, Qokeedy is only the 15th most common word here, while in actual Courier B, it's the 6th most common word. Judging from the words that rank above Qokeedy in the simulation, the difference appears likely to be due to higher frequencies in it of very short words. In real Voyniches, there seems to be a reduced probability of spacing adjacent to one or two glyph sequences, which I didn't factor into my generative model. Meanwhile, the same stochastically generated text also features the same extended networks of related words identified by Torsten Timm with relative frequencies in similar proportions. And it even fills in some of the unattested words that Timm lists, always with very low token counts consistent with relative improbability. Overall, generating text based on these second-order transitional probability matrices seems to replicate the actual vocabulary and relative word frequencies of Voynich's surprisingly well, although that the dynamics of this are all still somewhat mysterious to me. But something I find even more thought-provoking happens when we constrain the same generative algorithm to allow only transitions with a probability greater than some threshold percentage. Here's an example generated with the threshold set to 50%. That is, we only allow the top 50% of most probable transitions from each glyph or each bigram. You'll notice that not only does the text become conspicuously repetitive, but it also fixates on the same exact word forms we find repeated in notoriously repetitive sections of the actual Voynich manuscript, such as Choir 13. One intriguing hypothesis these observations suggest to me is that maybe the default behavior of Voynich's really is to repeat by looping in particular predictable ways. The less information any given sequence encodes, which is to say the less entropy it displays, the more closely it would then conform to these default loops, and the more conspicuously repetitive it might appear. Conversely, the more information it encodes, the more the looping pattern might give way to meaningful signal. It might not look so repetitive. Meanwhile, as we've seen, the frequencies with which specific words and glyph sequences occur are at least roughly proportional to how closely they conform to this default looping behavior, which, according to this hypothesis, would make their frequencies inversely proportional to how much information each one individually encodes. The information in Voynich's would then seem to need to lie in the deviations from these loops. Whether these would be meaningful information or not, I don't pretend to know. I could talk further about possible cipher mechanisms that might lead to patterns such as these. Other things I've investigated are the effects of considering not just second order transitions, but also third, fourth, fifth, sixth, and seventh order transitions. But I tried to pick something I thought I could cover in about 20 minutes. And so with that, I'd like to uh, transition to Q&A, although I don't know that questions and answers are really the proper way to think about this. I don't know that I have a whole lot of answers, but maybe at least to some discussion. Thanks for your kind attention.
Thank you, Patrick. That was really interesting. Um, yeah, I think in things like this, it's mostly questions and further questions rather than questions and answers. Um, it's again not my specialty, but it almost felt like at some point, like you were thinking about that they were like rolling dice or something, like kind of. Does it just feel more? Mm, like almost like they used some kind of mechanical system that determined a certain like greater odds for certain things to happen, or am I misunderstanding?
No, no, that's so again, I didn't talk much about the the potential implications of these
Mm,
patterns. What you're describing makes sense. I mean, one thing that I like about this analysis is that it does take a fairly simple set of rules, if you will, just these uh, percentage probabilities of transition from one glyph to another. And these have these cascading effects on the results that end up looking very complex. And it does perhaps seem as though it would be consistent with some kind of a random method of generating text. That's certainly a possibility. I wouldn't want to exclude it. But then personally, I also have a preference, a completely subjective preference for solutions that end up containing some kind of meaningful
Mhm.
message. And I don't see what I've described as being inconsistent with that. Uh, possible cipher mechanisms that could produce a result like this. One that occurred to me is if in each transitional probability matrix, the transition that occurs most often,
Mhm.
so Q to O, for example,
Mhm.
or in Courier B, E to D, would behave as a null. Then you'd have a series of other possible transitions that would each encode something
Mhm.
meaningful. So you at each point in the loop, you'd have the option of encoding particular values. But if you didn't want to encode any of those values, you'd use the default, the null, and then move on to the next step in the sequence. So
So it's more
some
like
pattern. Mhm.
you would have to spot the unusual parts to find the meaning, if I more or less. Is that what you mean, or?
Right. So if you remember the screen where I showed all of those
Mhm.
most uh, those longest repeated segments, that the content could be encoded just in the deviations from
Mhm.
the loop. And of course, in most cases, there would be more deviations and more content. So it may seem like it's a set of analysis or a set of analyses that seem consistent with some kind of meaningless stochastic process, but I don't think it needs to mean
Mhm.
that. I think it could have other explanations.
Okay. We have a number of questions in the chat. If you could have a
Oh,
look at those.
sure. Let's see. Back to the beginning here. It was okay. More or less likely to be meaningless. Uh, so yeah, so yes. Now we need something that explain how this fits in with all of the wonderful line and paragraph patterns. And I do have some thoughts about this. I didn't include them in the presentation because I just didn't think there was time to go into so much. As I mentioned, I've not just looked at these first and second order transitions, but also third, fourth, fifth, sixth, and seventh order transitions, going up to for every sequence of six glyphs, what's the probability of what the seventh one will be? And this is really uh, unpleasant to have to do. You end up with spreadsheets containing millions of lines. Uh, and I don't know that I want to go a whole lot into detail about this, but one thought I had was that there could be mechanisms by which, if each new glyph depends on the glyphs that came before, this might not be symmetrical, so that the probabilities of glyphs might change cumulatively over the course, at least of a line, so that the probability of so just to give one example, one thing I found was that a gallows glyph makes glyph a little bit less likely for a few spaces, but then a few further spaces along it becomes more probable. And yet it becomes more probable for the same gallows glyph to repeat, but also a little more likely for other gallows glyphs to repeat. This is a fairly typical pattern that seems to exist there. So, but the overall pattern is that if you once have a transition away from the loop, that same transition tends to become more probable as you continue on through the line. So that wouldn't explain all of the line patterns, but I thought that possibly some way in which the cumulative result could add up over time, making certain transitions more or less probable, that might contribute to patterns like that, at least.
Mhm.
One
Yeah.
possibility.
If I may add a comment, if you can hear me.
Yes.
Renee here. I mean, I'm sure this is useful information, but I'm also entirely sure that this wasn't in the author's minds when they wrote the manuscript. So it is the result of something, but not planning to do this, obviously. And the one thing I got from Davi's presentation is that there are things in there that are very far from arbitrary. It's not just random, stuff. So yeah, lots of data. It's difficult, but I mean, I agree. It's interesting to look at these statistics, and I still agree also that your talk in the Malta conference shows a lot of data that we still don't understand. I don't understand it. And there's something there that may help. It's likely to help if we know how to do it.
Let's see, going down the list here. Lisa asks, how do I account for P and F and top lines? Uh, so I'll say, first of all, this hypothesis I just laid out here is frankly incompatible with all kinds of other hypotheses I have. I think a lot of us have to juggle lots of different ideas that don't really seem to fit with each other. I don't have any explanation within this particular model for P and F, except that if the formulation of a line is cumulative, that would account for why the presence of a P at the beginning of a paragraph might affect the composition of the line from there on out, making another transition to a P or to an F more probable. That's one possible way of looking at that. I do wonder. I'd thought about trying to run a simulation of what this kind of analysis would look like for English, and then what a randomly generated text would look like based on the patterns for English. I didn't do that, but it would be really fun to try.